Okay, so the next talk is about simple and effective noisy channel modeling for neural machine translation. This is presented by Michael.
Hey, thanks everybody for coming. So this is work that was done during an AI residency. And nowadays, all of our models are direct models. And the way they function is that we give some type of input. So let's say here this would be a German sentence. And that is being processed by our neural network. And then we directly output a target sequence. But not so long ago, the main paradigm in statistical machine translation was making heavy use of indirect models or channel models. And the way they function is that they would look at potential targets and try to map them back to the source. So we would in some sense try to explain the input given the output that our model is suggesting. So how does it work? Well, we simply apply Bayes' rule to decompose y given x, and we can ignore the denominator because it is constant for all possible y. And then the only thing we need to model is the probability of x given y, which I will call the channel model, and then the probability of y, which is usually parameterized by a language model. So now you might ask, well, we have very good direct models, finally, why go back to this indirect approach? And I'll give 3 reasons why this might be a good idea. So the outputs of our neural network text generation models is sometimes not related to the input. So sometimes these models generate spurious outputs. So they add information that is not present in the input, for example, in translation, or they might just start stuttering, so they repeat outputs. Now, if we had an approach like this, which requires our outputs to explain the inputs, then we might actually mitigate some of those problems. Next, language models in neural machine translation have been far less successful than they have been in the statistical machine translation era. And the noisy channel approach might help us with that, as I will show. And then finally, from a practical perspective, these models can perform really, really well, as shown in this year's WMT submission. So how can we parameterize channel models? Well, recent work from a few years ago has suggested to use this segment-to-segment transduction model. And the way this simply works is by learning a latent variable model that reads part of the target we would like to assess, then makes a decision on whether we are ready to emit the first source symbol, and it does that. And then it might read more of the target and output the next source token and so on. So it does this in this, it basically processes the target and source sequence in this segmental fashion. So the approach that we follow in this paper is a very, very simple approach. We just reuse our standard seek-to-seek models. And the way we do this is we take potential outputs that are suggested by our decoding procedure and then feed that into a standard seek-to-seek model, so in our case a transform model, to score the entire source. And we do this for all possible prefixes of the target that we consider, as shown here. And crucially, we always score the entire source, which is different to the segment-to-segment approach, which only scores part of the source. So what we do is, as I said, we just use the standard approach to train the seek-to-seek models. Instead of training it to predict the target given the source, we predict the source given the target. And then we use that model to score the full source given partial targets. Now, of course, there's a clear training and test mismatch because this model that was trained on full source target sequences has never been exposed to partial targets. But empirically, I will show later in the talk that it still works very well and is a testament to how robust these models are in practice. So putting these two approaches side by side, we have a specialized latent variable model on one hand, versus we have an out-of-the-box model on the other hand. So that enables us to use the latest advancements in seek-to-seek models. Also, the segment-to-segment model is an online model, and being able to process data online comes at a cost in terms of accuracy. So at the time, this model was far less accurate than a standard attention model. And as I said earlier, one has to explain only a prefix of the source versus the other one scores the entire source. And that might be useful for languages where the word order differs significantly. Now, the segment-to-segment model has a linear runtime in the source and target length versus the standard seek-to-seek approach in the way we use it at inference that I showed earlier in animation. There's a quadratic running time. But in practice, we can batch the scoring of all the source tokens. So we can batch over the time dimension here for once. And that mitigates a lot of that runtime complexity disadvantage in practice. So let's look at a bunch of experiments. So first I want to motivate why it is useful to score the entire source with the channel model as opposed to just parts of it. So what I'm showing here on the x-axis at the bottom is I'm showing the accuracy of feeding various target prefix lengths into our model. So on the very left-hand side, you have about 10% of the target sentence. On the right-hand side, you have the full target sentence. And then on the top, or the lines that I will be showing rather, is the performance of scoring parts of the source sentence. So about 20% up to the full source sentence for each of those prefixes. And what we can see is that for all but the very shortest target context sizes, scoring the entire source works best. So clearly, really trying to explain the entire source empirically works better. Next, how does this noisy channel approach compare to some strong baselines? Well, so the first bar here is a direct model. That's your standard seek-to-seek model that maps the source to the target. Then we have an ensemble of 2 such direct models, because the simplest thing to improve performance is to just have 2 of those models, and then the language model. So adding a language model to your direct model. And then another baseline is these right-to-left models that people use in rescoring very often. So they also perform very well. They get a nice boost from adding a language model. And then finally here on the right-hand side, most right-hand side, we can see the noisy channel approach here with the direct model, the channel model, and the language model. And we can see 2 things. So first of all, adding the language model really makes a difference here. So it's not the channel model that is the driver of performance, it is the language model. And the role of the language model is, in some sense, to mitigate explaining away effects of the language model. So because adding it really makes a big difference. Okay, finally, what this shows here is the accuracy when we increase the search space. So here in a re-ranking setup, instead of looking at best list of size 5, we consider up to 100. And the most interesting thing here is that if you look at the bottom, increasing the beam size for a standard seek-to-seek model, so the direct approach in black, there's no difference increasing the beam size. But the channel model approach can really exploit that larger search space a lot. So we can gain 2.5 loop points by simply increasing the n-best list size. The right-to-left model also can add something, but it's not as much. So the channel model is really very good at exploiting larger search spaces. Okay, then from a practical perspective, so there's all of this work when we apply it to really strong competition systems. And the answer is yes. So what I'm showing here is the performance of our WMT submission this year for English or German with various improvements. So we have like back translation here, we have assembling here, etc. And at the bottom you can see, bottom left, you can see that the noisy channel really gives a nice and healthy improvement here on top of really, really strong models, so ensembles of back translation models that were trained on 500 million sentences. Okay, so to summarize, standard seek-to-seek models are a simple and highly effective parameterization of the channel model. And the reason being that they can exploit the entire source sentence. We've seen that the language model is really the main driver of performance, and the role of the channel model is to mitigate explaining away effects. And that this approach can also be very effective on top of strong baselines. Thank you.
Thank you very much. I think we have 2 minutes for question answer. Any question?
Very nice talk. I'm wondering it performed very well. I'm over here, by the way. Performed very well on WMT19 English-German, which is entirely source original, forward translated test sets. Do you know whether it also performs similarly well on target original test sets?
Yes,
okay.
because the humanly valid WMT also included those sentences. So yes, and at this year's at this year actually, it was all the test sentences were all source original, right?
Yes.
And it did perform very well there according to humanly valid.
Anything else? Okay.
Yes, I'm here.
Okay, very quick question. So at the beginning you said you integrated in decoding, but at the end you only reported on results with re-ranking. So is it necessary to do it during decoding?
No, we ran most of those experiments in re-ranking simply because that is faster to do, but in the paper we also have decoding experiments that mirror a similar image. Yeah.
Yes.
In fact, actually, the experiment that showed that you get larger improvements with larger n-best list sizes is very encouraging to work more on decoding.
Maybe you want to say a word about the integration with the language model? Which kind of language model did you use, and how easy are they to integrate with your search?
So the language model is the easiest thing to integrate because it factors exactly over the the target sequence. It just scores the target sequence similar to the direct model. And the type of language model we used, it was a standard transform model with, I don't know, like 12 layers or something like this. So it was a pretty beefy model. And for WMT, I think we trained it on a lot of sentences. It was a very large scale model with like hundreds of millions of sentences. Even for the other experiments, I believe. Yeah.
Okay. We're running out of time, so thank you very much.